Hi, everybody. Welcome to today's edition of the Spectral Geometry in the Clouds seminar. Today we have Jeff Galkowski from UCL, who will tell us about the Steklov problem with piecewise smooth boundary. As usual, if you have questions during the talk, just unmute yourself and ask them or put them in chat and we'll relay them. Jeff, the floor is yours.
Thank you very much for the invitation to speak here or virtually here today. I sort of swore I would never give another online talk, but here we are again. Anyway, so today I'm going to give a talk about some work that we've been doing for about a year with two of my postdocs, Marcello Malagutti, who's here at UCL, and Wang, who's now a postdoc at Yale. And this project is about the Steklov problem, as I say, with piecewise smooth boundary. And for full disclosure, most of the results as they apply to the actual Steklov problem on a compact domain will be in 2 dimensions today. But the hope is that going forward, this approach will be useful also in higher dimensions. So let me remind you what the Steklov problem is. So many of you, of course, are familiar with this, but just in case, let me remind you what's going on here. So we have some compact manifold with, say, Lipschitz boundary. And what we're interested in is solutions of the following spectral problem. You want a harmonic function in the interior of your domain, and you would like to find, functions which satisfy the so-called Steklov boundary condition, that is, their normal derivative is a multiple of the Dirichlet value. And of course, one can rephrase this as in terms of the Dirichlet to Neumann map, which I define as follows. So just again, to remind you, you want to solve the harmonic extension problem. So I take the harmonic extension of some function on the boundary, and then I ask, what is the normal derivative of that function? And that's the Dirichlet to Neumann map. So this is very familiar. It has applications in physics as the voltage to current map, which appears in inverse problems. The Steklov problem itself appears in the linearization of some water waves problems. So this thing really does appear in nature in some sense. And so the question is, what are the eigenvalues, and if you wish, eigenfunctions, or their harmonic extensions of the Dirichlet to Neumann map, right? So that's, if you wish, the Steklov problem. What are the eigenvalues and eigenfunctions for the Steklov, for the Dirichlet to Neumann map, as well as their harmonic extension, right? And so I am a high energy person, so I'm going to be interested in what happens as this eigenvalue goes to infinity, right? So I want to know, how do the eigenvalues behave, for example, as the energy or the eigenvalue tends to infinity. And you can also ask similar questions about what does the eigenfunction itself look like. And the way I like to, again, think about that problem is as the energy tends to infinity. Right, so, okay, you could ask also about the restriction of the eigenfunction to the boundary, but you want to, or I want to think about this in terms of 2 different properties: oscillations, so how quickly does this function, oscillate, and decay. All right, so these are 2 natural notions of what does a function look like. And before we go too far in the world of rough boundaries, let's talk about this problem when there's a smooth boundary. So in that case, we know really a lot about the Dirichlet to Neumann map. We can describe it in terms of the pseudo-differential operator, and you know its symbol. You know, in principle, you know all the terms in its expansion in terms of derivatives of the metric at the boundary. And so what this lets you do is use the big machine of microlocal analysis, for example, to study eigenvalue asymptotics. So in general dimension, you have the standard, or now standard, Weyl asymptotics. Namely, you have the top term of the asymptotic expansion for the eigenvalue counting function plus 1 order down. And if the dynamics of the geodesic flow on the boundary are sufficiently nice in some sense, then you can improve this in various ways. So for example, if you have 0 measure set of closed geodesics, then you can get a small O improvement to this. Okay, And when d is 2, you can do much, much, much better. You can actually label the eigenvalues modulo j to the minus infinity. I believe this was due to Rosenblum in the first instance. And so, of course, this is a fact because the boundary is one-dimensional, and one-dimensional spectral problems are somehow much simpler in this way. But nevertheless, it's a little surprising that you can do this well in a non-local problem where the operator is really pseudo-differential. So that's sort of the answer to what do the eigenvalues look like. You might also, as I said, be interested in what the eigenfunctions look like. And one thing is that the restriction of the eigenfunction to the boundary looks like a Laplace eigenfunction with eigenvalue sigma j squared. Okay, so that's one thing. And you can see that in these pictures by, maybe in one dimension, of course, the Laplace eigenfunction is nothing but a plane wave, and it oscillates just as you go around the boundary. And you can sort of see this in these pictures. These are the positive and negative sets of the eigenfunction and its harmonic extension. But nevertheless, so at this moment, many of you could be asking, well, these things look a lot like Laplace eigenfunctions. What is really the point of doing this Steklov thing if everything is going to be the same? But it's really quite different in a number of ways. So the first and maybe most obvious thing is that if you think about the harmonic extension itself, you'll see that it decays very, very fast in the interior here. So, okay, in this picture, green is sort of small and blue and yellow are big. So you see that it's, okay, of a reasonable size at the boundary here, but then it decays very, very fast into the interior. And actually, Hislop and Lutzer showed that this is super polynomial. In the general smooth case, if it's analytic, you can get exponential decay, and that's due to Toth and myself. And maybe what's more surprising is that if you stare at these pictures, you'll see that the oscillations are very fast near the boundary, but very slow in the interior. And this is really true in at least some dense set of simply connected domains. Okay, so you do see new behavior even in the smooth case. Okay, so you might be interested then in what kind of new phenomena you see when the boundary becomes rougher, right? And so let's start down this path and let's ask ourselves, what can we say about these various things when the domain has Lipschitz boundary? So again, we started with the fact that the Dirichlet-de-Neumann map in the smooth case is a pseudo-differential operator of order 1. So you could ask yourself here, what is the structure of the Dirichlet-de-Neumann map for a Lipschitz boundary? And many of you would say, well, that's far too greedy. Lipschitz boundaries are horrible. You're probably not going to be able to say much, and you would be right. But you can still say something about the eigenvalue asymptotics, and this is a relatively recent work of Lagasse, Karbuk, and Polterovich in dimension 2, and then generalized to any dimension by Rosenblum, that you still have top order Weyl asymptotics. So you don't get a full term down, but you still get a little O improvement to the Weyl asymptotic, or sorry, a little O asymptotic formula for the eigenvalue counting function. Okay. You might ask, what do these functions look like? And the answer is, we don't know, really. This is a very complicated problem when the domain is Lipschitz. So let's make our lives a little bit easier. Let's go to the piecewise smooth Lipschitz case. So here, you probably think there's some hope to understand these things, right? So the singularities are sort of isolated. Everything is a bit nicer. And this is the setting in which I'm going to work for the rest of the talk. So again, you can ask, what is the structure of lambda? And sadly, the answer is still the same. We don't really know, right? But we're going to work on that. You can ask about eigenvalue asymptotics. And in general dimension, the best we have is still this result of Lagasse, Karpuk, and Polterovich, and Rosenblum. You have the top order term. So when can you say something better? And sorry, the eigenvalues and eigenfunctions, again, we don't know. So we would like to sort of fill in this slide, right? That's sort of the goal, a big goal you could have in the world of Steklov problems rough domains. We do know some things. So as I said, very little is known except in a few special cases. In dimension 2, there's very nice work of Levitin, Parnovski, Polterovich, and Sher, where they study piecewise smooth Lipschitz boundaries with angles less than pi. I'll explain that in some more detail a bit later. In higher dimension, even less is known unless you're a cuboid. So there's work of Girard, Lagacé, Polterovich, and Savo, or very recently products of balls in an interval by my student Blount. And those are, those two cases are really special because you can separate variables and you can really get your hands dirty with special functions and that sort of thing. So we would like to go beyond this, right? We'd like to go beyond dimension 2, although, as I said, I won't go very far beyond that today. We definitely, and we'd like to study things that are not easily separated. Okay, so now let's pause for a moment and ask ourselves, what do these eigenfunctions actually look like on a piecewise smooth domain? So I have here some pictures I made in FreeFem, and these are, okay, I didn't pick any particular sequence of eigenvalues. I just wanted to sort of display the behavior. So what do we see in these pictures? We see, again, near the smooth parts, you see nice sort of regular oscillation. So anywhere on these smooth parts, except you notice here, everything disappears, maybe. And you can see, I should say that purple and green are big and blue is small. That's important. So here, actually, the purple and green, you can just barely see them. They're over there. So you can avoid this section, or you can live entirely there. You can live in this hole in the middle. And otherwise, you see a smooth thing, something happens at the corner, the amplitudes sort of change, you go around, the amplitudes change. Here, somehow nothing goes through, and that's maybe what you notice. Another thing to point out here is that if you sort of stare at this, at least with a loving eye, you'll see that near this corner here, the eigenfunction tends to spread further, say, than near maybe a right angle corner or this corner here. So you'll see that this little nodule is larger. And actually, Marcello explained to me that this is related to how lightning rods work. So the sort of, it's not possible to maintain a very big voltage jump near a lightning rod, and this is sort of related to that, because remember, this is the voltage to current map. Okay, so this is what these eigenfunctions look like in a numerical simulation. Again, the things I want to highlight are that near the smooth parts, everything sort of looks like it looked like in the smooth domain, and then there's some kind of interaction with the corner. So now I'm going to be talking about a small generalization of the Steklov problem, which is the positive mass Steklov problem. So instead of a harmonic function in the interior, I'm going to be taking, okay, an M harmonic function. So that is to say, Laplace plus M square U sigma should be 0. And I'll explain why that's a natural thing to do a little later. But for now, let me just say that that's what we're going to do. And so I want to study this positive mass Steklov problem on this piecewise smooth Lipschitz domain. So you'll notice that I'm allowing here angles that are big in principle. Everything can be curved into the corner, and so on. Okay, and in principle, I could have a hole in the middle, but I don't draw that here. And so what I want to do is I want to introduce a Dirac operator on the boundary of this domain. So if you like, I think of this boundary as a metric graph, right? So each of these edges has a length, and then you know who it's connected to. And this Dirac operator is then just this simple Dirac equation on each of the edges with some kind of matching condition at the corners. Okay, at the interfaces between two segments. Okay, and the way this matching condition looks like is that you'll notice that this Dirac operator solutions to d minus lambda are again columns of plane waves, one going left if you wish and one going right. And this matching condition is a matching condition between the things that are going in to this corner and the things that are going out. Okay, so we have a Dirac operator with some matching condition at the corners, and then we have the Steklov problem. Okay, and the theorem is that the spectrum of these two operators is related. And I'll display the theorem of Levitin, Parnovski, Polterovich, and Sher in just a moment. And it's sort of the same flavor. They gave many equivalent formulations of this thing, but I'll just stick with this one. So what does this thing say? This says that the eigenvalues, and in fact, in some sense, the eigenfunctions of the Steklov problem are more or less the same as the eigenvalues or non-negative eigenvalues of this Dirac operator. And okay, this S alpha, you can compute it explicitly in principle. Yes. And if you wish, and this is what I'm going to call the scattering matrix at the corner, and that it will become clear why that's the case. And this G alpha is related to some Hardy constant, which I'll also explain. But the moral of the story is that, again, the eigenvalues are close to the eigenvalues of this Dirac operator on the metric graph with matching condition given by this scattering matrix. Okay, and the quality of your approximation depends on two things. It depends on the size of the angle. So the smaller the angle, the better this part is. And actually, the smaller the angle, the better this one is too. But unfortunately, this Hardy constant has an upper limit of a half. So that's how it is. So the best you can hope for is that these are the same modulo sigma inverse, almost. Okay, and if we compare that to the result due to Levitin, Parnovski, Polterovich, and Sher, there are, okay, again, the story is the same. They found a Dirac operator or a number of other different characterizations of these eigenvalues, or quasi-eigenvalues, if you wish, under a few differences. So maybe one assumption I want to point out is that the angles are less than pi, and that's, if you want, because this number here degenerates as the angle goes to pi. Okay, they studied the m equals 0 case, and okay, the quality is a little bit worse, but I don't think we should take this one half that seriously. So the thing I want to talk about is the difference of the approach. So these folks took the approach that they had some more or less explicit solutions, which were found quite a long time ago by Peters, and they were able to use those solutions to construct a lot of quasimodes, enough quasimodes actually to know that the system was asymptotically complete. And that is really, quite a remarkable piece of work to be able to do that sort of with your bare hands. I'm going to take a somewhat different approach, and it will hopefully generalize also to higher dimensions. So I remind you now of these pictures, right? Again, the point is, it looks like a wave near the smooth domain. Something happens at the corner, and then smooth domain, something happens at the corner. And if you were to stare at this for long enough, you might be able to convince yourself that the matching condition at the corner is exactly this scattering matrix. Okay. So how could we get to a point where we can do this not just in 2 dimensions, but maybe also in higher dimensions? Okay. And what I want to do is I want to take this idea sort of much more seriously, that this problem looks like the smooth thing near a smooth part of the domain. something happens at a corner, and then you can try to connect those up. So what do I mean by that? So, okay, I'm going to use the word blow up, even though I don't like it. It's just rescaling. But so what you want to do, or what we're going to do, is we're going to think of this problem like I said. So near a smooth part, it should look like a smooth thing. Near a corner, it should look somehow different. And the way you understand what it looks like is you try to zoom into the singularity to a what I'll call local scale invariant model. So I'll draw some better pictures of this in a second. But again, you can imagine you have some curvy thing like this. And then if I zoom in at this corner, right, what happens? Well, I zoom in at this corner, it gets somewhat less curvy. Oops, sorry. Somewhat less curvy. Right now it's more like this. And eventually it's very, very close to this infinite sector. All right, and that is scale invariant because if I zoom in, I just get the infinite sector back. There's nothing more I can do by zooming in. That's all there is. And okay, so that's the first step you want to do. You want to zoom in at the corner, and you want to try to understand what is the local scale invariant model. Okay. And then once you're in the model, you want to study scattering on it. So I'll explain in some detail what I mean by that. But roughly speaking, you should think that scattering is about the following thing, right? So here's my local scale invariant model. I want to know if, in some sense, I send a wave in, say, here and here, what comes out, right? And that is the notion of scattering, which I'll explain, right? So that's somehow the thing which gives you this matching condition at these corners. You want to really, again, take seriously this idea that the only thing that matters is the sort of asymptotic structure as you zoom in on this corner. And really the only thing that matters is this scattering. So now, okay, so once you do that, I lie here a little bit. You need to do this on an approximate model. So, okay, I'm going to sweep that under the rug for most of the talk, but just to say it's an approximate model. Okay, and then you need to glue your model back into the compact problem. And this is quite tricky because we're all sort of used to gluing solutions together when operators are local, or at least close to local. Here, the operator is rather far from local. And again, I will try to explain how you go about doing this. Okay, so that's the approach I want to advocate for. So I'm going to talk about it mostly in 2 dimensions, but the goal of this program, if you want, is eventually to do this hopefully in higher dimensions and see where we can get. So again, what do I mean? I want to zoom in and get this local scale invariant model. So here's my favorite piecewise smooth Lipschitz domain in 2 dimensions, and I grab one of these corners, right? And as we discussed, the asymptotic problem is on an infinite wedge of angle alpha 0, right? So these things meet at some angle alpha 0, and the asymptotic problem is this infinite wedge of angle alpha 0. And I want to do this rescaling so that I remain with a positive energy here, right? So I want to sort of really talk about the Steklov problem. So I scale by sigma, and that means I have still a Steklov problem, but now with energy 1. And you'll notice that the mass rescales like that, and that's going to come and be important later. So in particular, if you want to study high energy things, you must study small mass. You cannot avoid that. Now, okay, you could still ask me, why do you want to think about this mass at all? So for that, let's ask ourselves, okay, suppose we start with no mass whatsoever in the 3 dimensions. So now I'm thinking about the Steklov problem on this sort of bell-shaped thingy, right? The interior of this bell-shaped thingy, you have a harmonic function, and I solve the Steklov problem on the outside. So now I grab some point where the boundary is singular. Okay, and you zoom in the same way. Okay, so now you zoom in and you get this, infinite folded piece of paper, right? So I have a harmonic function in the interior of this sort of inside the folded piece of paper and the Steklov condition on the boundary. Okay, but now this problem has an extra symmetry. It has a translation symmetry. So, whenever you see a translation symmetry, we all know what to do. We take the Fourier transform. You can't resist it. It's like, I don't know. Anyway, you can't resist taking the Fourier transform. And then you quickly see that, well, now I've reduced myself to the two-dimensional problem, still with the same Steklov boundary condition, but with a positive mass. So if you want to solve this higher dimensional problem, you're forced to study the Steklov problem in some sense on a wedge with positive mass, and not just some fixed positive mass. You need to do this with small positive mass, with large positive mass, whatever mass you so desire. Okay? So this is, in a way, why we went down this road of studying the problem with positive mass, because if you wish to do this, then you must somehow handle this problem. Okay. So this was the first step, right? So you think about what is the local scale invariant model. In this case, okay, you got here, this is scale invariant. There was an extra symmetry you could reduce to here. In the two-dimensional case, you always get an infinite sector with some particular angle. Okay, so now I promised you I would tell you what do I mean by scattering, and I'll try to give you some details without giving all the details. Right, so again, hopefully I convinced you that studying the positive mass problem is natural and at least relevant if you want to do things in higher dimensions. So I'm going to stick with that problem from now on. And now I want to study scattering for the Dirichlet-Neumann map, right? So I'm thinking about now the function really on the boundary. And I imagine somehow doing an experiment where I send in a wave from infinity, one from the right, one from the left. All right, and okay, already I've sort of done something a little bit sneaky here, which is I'm claiming that this guy at least approximately solves the problem near infinity. This is not a priori obvious because this operator is in general highly non-local, but let's suspend disbelief for the moment. This thing does in fact approximately solve the problem near infinity, and so you want to correct this thing to an actual solution of the Steklov problem, right? So you would like to know that there is a unique outgoing thing, so now going in the other direction, which now honestly solves the Steklov problem. Okay, and again, this is really asymptotically near infinity. It should look like this. So this is, if you wish, the problem we would like to solve, right? So you send something in, you ask what comes back to you, right? And again, if you believe this story I told you, which is that things look like the smooth problem until you get to the corner, the smooth problem has solutions exactly like this. Then something happens at the corner. It's not totally clear what, but if you believe that this local scale invariant model is the right thing, then the way that the incoming part of this solution on the smooth part is related to the outgoing part on the smooth part should be exactly this, whatever I mean by scattering on this infinite sector. Okay, so that's the goal, if you wish, of doing this scattering theory on an infinite sector. Now, there are a number of questions you might be asking yourself. So first of all, in order to do this, I need to define the Dirichlet-Neumann map when m is 0, or at least when m is small. Okay? So when m is positive, the Dirichlet problem on this infinite wedge is well posed. Right, this is a nice coercive quadratic form. Everything is wonderful. It controls the H1 norm, and so you can solve the problem. But when m is 0, this is no longer the case. This does not control, it's not true that there's a constant so that C gradient U square controls U and H1. This is no longer the case, right? This is not true. Right? So you cannot solve the problem using the standard lax milligram thing. So, and if you want to have, a well-defined Dirichlet-Neumann map, then you'd better have a well-defined harmonic extension. If you can't do that, you're in trouble. Okay, so it turns out that in order to do this, what are known as these Hardy constants matter. So what is the Hardy constant? The Hardy constant is the best number so that this estimate is true. So you don't request that the gradient control all of the L2 norm. You request that it controls some weighted L2 norm, right? So this is for U, I should say, in H01 of the domain. And there is such a constant. And one can say a lot about the best such constants. And there's some very nice work of Brian Davies that we're using to describe these things. But you have such a constant. And once you see this, it's very natural to try to work in weighted spaces, right? It's very natural to try to somehow weight things as you go away from the boundary. So if you'd like, I can talk about exactly what these spaces look like, and I'm sure we're not the first people to do this, but anyway, in this particular way, I'm not aware of a reference. So we're going to define the harmonic extension on some weighted L2 based spaces, and that's going to allow us to find a limiting absorption harmonic extension as m goes to 0. Right, so you'll notice, of course, that when m is 0, you're in the spectrum of the Dirichlet-Laplacian, so you've got to do some limiting absorption type argument to get a harmonic extension when m is 0. And okay, you might say that, well, why don't I just take the bounded one, the bounded harmonic extension? I mean, this is a thing you can do, but it's not particularly well behaved in sort of a functional analytic sense. Okay, so and this G omega actually controls how much weight you can put on this function, and in particular, this G omega gets okay, I think I may have done the inverse, but anyway, this G omega gets bigger as I've written it as the angle gets bigger. So you need more multiples of the gradient. And that's actually why you see this phenomena that the bubbles grow bigger as the angle gets bigger. Okay, so then once you've described what this Dirichlet-Neumann map sort of is, that it exists, you would like to know, in order to do scattering theory, what it kind of looks like, right? So what I mean by this is that, in a way, scattering theory is about what happens at the various infinities. So here there are two. There's the frequency infinity and the physical infinity, right? So the thing that's, fortunately, this Dirichlet-Neumann map is more or less elliptic. It's elliptic at the frequency infinity, but it is not. It's not really elliptic at the physical infinity, and so what's important is what it looks like near the physical infinity. That's sort of the new thing, because you'd like to describe that so you can find then spaces on which to do scattering theory. Okay, and one of the big challenges here is that, again, this Dirichlet-Neumann map is highly non-local, right? So what happens very, very far this way affects in a non-trivial way what happens over here, okay? And that makes somehow dealing with these things a bit more challenging. Okay, so now let me tell you what the theorem says. So you have an asymptotically conic domain with piecewise smooth Lipschitz boundary. So let me tell you what that actually means. So I'm going to grab y, let's say, inside the sphere. This is some open domain with smooth boundary. Okay, and then the model for this thing near infinity is the cone over y, right? So the cone over y is sort of your model. So near infinity, it looks just like the cone over y. So okay, if I draw this in a picture, I'm thinking of something like this, right? Think of the interior of this cone. Okay, and then what I allow to happen is I allow that down here, I can have some horrible Lipschitz singularity, right? Whatever, it can go badly near the pointy end. The infinity must be sort of smooth. Okay, at least for the moment, and that's one of the obstacles one has to deal with if you want to go to higher dimensions. Yeah.
Quick question.
Yes.
So y has to have a smooth boundary here, not piecewise smooth?
That's right. Y has to have a smooth boundary. So
Got it.
if you want to go to higher dimensions, of course, you need to deal with that problem.
Eventually.
But right now, smooth near infinity. So if you like, I mean, one thing you can do is the honest to God cone, right? That's allowed. Okay. So you have this this asymptotically conic domain with piecewise smooth Lipschitz boundary, and you want to look at its spectrum. Okay, and what happens is that you have, it's been known by some work of Pankroshkin and Khalil that the continuous spectrum starts here at M and goes to infinity. And they studied eigenvalues down here below this M. And what we can show is that the set of eigenvalues above M plus delta is discrete. In general, we don't know whether it can accumulate at infinity. We don't know whether it can accumulate at M, although I seriously doubt it in nice cases. But at the moment, we don't know. But away from these eigenvalues, the limiting absorption resolvent for the Dirichlet-Neumann map exists as an operator on these spaces. You can describe, of course, much more sophisticated spaces on which this thing exists. but as an operator from L2 comp to L2 loc, this resolvent does exist. And in fact, in nice cases, so if the dimension is 2 and you have a piecewise smooth boundary, or the dimension is bigger than 2 and say you have the cone, then you know that there are only finitely many of these eigenvalues above M plus delta. Again, at the moment, we don't know really what's happening near M, although I would be very surprised if you can have accumulating eigenvalues from the right, at least. In fact, if I had to guess, I'd say there are probably no eigenvalues in the continuous spectrum at all. But again, we can't show this. Okay, so this is what the spectrum of the operator looks like, say in dimension 2. You have continuous spectrum starting at M. You have finitely many eigenvalues above M plus delta. You have, of course, finitely many eigenvalues below M minus delta, and then we're not quite sure what happens here at M. Okay, and what that lets you do is it lets you define the scattering matrix. So what I mean by that is, again, I think of my asymptotically conic domain. Again, for the moment, that thing has a smooth boundary near infinity, right? And that's right now I'm calling the boundary y. The boundary near infinity is y. Then you can prescribe a function in L2 of y, which is going to be your incoming wave. And you can solve the problem lambda m minus omega u is 0 with that prescribed incoming data. And there's a unique outgoing data, okay? So, okay, the actual solution is unique up to eigenfunctions, but the eigenfunctions turn out to decay super polynomially as you go to infinity. So this lets you define the scattering matrix at any energy, right? So the scattering matrix itself is the map from this G minus to this G plus. And when the domain is two-dimensional, of course, that's an honest to God matrix, right? And in the model, when you have a scaling, you're actually in the infinite sector, this scattering matrix is exactly the scattering matrix that we wrote in the first theorem. Okay, but in principle, actually, one thing that's sort of nice is that the only time I need to know about explicit solutions of the problem is to write the formula for the scattering matrix. That's the only time we use it, right? So everything else is done via estimate. So if I don't care what exactly the formula is for the scattering matrix, I just want to know there is some unitary matrix, then I never need to know explicit solutions of the problem. Okay, so now that's the theorem, right? So you have a limiting absorption resolvent away from eigenvalues, and you have a scattering matrix. Okay, so now, in order to really do this scattering theory, I told you that you need to know what does this Dirichlet-Neumann map look like. And again, I'll go back to those pictures, right? So we believed, if you believe the pictures anyway, that near the smooth parts of the domain, this looks just like a smooth Steklov eigenfunction. Okay, so that could lead you to guess that also the Dirichlet-Neumann map on this infinite sector should look like the Dirichlet-Neumann map for the half plane, near infinity. And so that's our guess, is that this thing looks like the Dirichlet-Neumann map for the half plane plus an error. Okay, and the question is, what is this error? So before we talk about what the error is, let's go to the half plane. How good could this possibly be? All right, so you'll notice that I have these cutoffs chi plus, which are localizing me near positive infinity, and chi minus, localizing near negative infinity. So how good could this possibly be? Well, one measure of that is what happens if instead of putting chi plus, I want to understand this guy, lambda m omega 0, chi plus, chi minus. All right, so that's a measure of the long distance propagation of this Dirichlet-Neumann map. I want to know what goes from plus infinity all the way to minus infinity. And this is actually an easy calculation that if you want uniform estimates as m goes to 0, the best you can do is the following. Okay, I don't vouch for the endpoints being not there as the best you can do, but at least other than the endpoints, the best you can do is that you can gain 1 power of x and only for s in this interval. All right, so you stick in something which when I multiply it by x to the minus s, it's in, say, L2 or any Sobolev space you wish. You look at it near positive infinity, you apply the Dirichlet-Neumann map, you ask what comes out near minus infinity, and it's a little better than what you put in, but not that much. And you can't push further than this, okay? So the best you could hope for is that E plus and E minus do this, right? The best you could hope for is that you have an error which gains 1 power of x. Now that by itself is not going to be good enough. So you have to think a little bit more about what this is really saying to you. So you'll notice that I wrote here, I gain as many derivatives as I want, right? And so, okay, this is telling you that in some sense, at least, this long distance propagation is near 0 frequency. Okay, and you can make this a bit more precise. And that should make sense, right? Because when m is 0, the place where this thing is irregular is exactly at 0 frequency. And the irregularities in the Fourier multiplier, that's what causes long distance propagation. So it turns out that you can improve this, and you can say in some quantitative sense that this error is only happening near 0 frequency. And the same remains true here. So if you're interested in the Dirichlet-Neumann map on an asymptotically conic domain, then near infinity, it looks like the smooth problem plus an error, which is a little bit better in x near 0 frequency and much, much better in x near high frequency, right? And now, once you know that, you're sort of in business because you have a good understanding of what's happening near plus infinity, you have a good understanding of what's happening near minus infinity, so long as you stay away from energy 0. And then, okay, something happens in the middle, which you're not quite sure about, but the only infinity in the middle is the frequency infinity, and this is a nice elliptic operator. So if you want to make a scattering theory, then you've got to find sort of spaces on which everything works. And okay, I'm not going to tell you that much detail about it, but the important place, so this is a picture of physical space and frequency space, and this gray blob is where the corner is, right? So there I don't understand a lot about the operator. But as soon as I'm outside the gray blob, and this you should think of as x equals infinity and x equals minus infinity. As soon as I'm outside of the gray blob, I have, a pseudo-differential operator, which I understand well. The only caveat is that near 0 frequency, it has, I don't understand it that well, but I have good estimates. Okay, and that lets you do microlocal analysis near infinity to find spaces on which everything works. So, okay, I'm going to tell you some key words. So you have radial point estimates near c is plus and minus 1 at x is plus and minus infinity. Okay, I'm not going to say exactly what that means. And then near x equals 0, because of this problem with low frequencies, the long distance propagation of low frequencies, you have to localize in the variable x times c. Somehow this is where you localize in the variable x times c. And that lets you do everything you want. So you essentially do elliptic estimates, but in this funny variable, and then you do some propagation near plus and minus infinity, and that lets you sort of push this into a somewhat standard toolbox. Okay, and then near 0, near x equals 0, you use the elliptic estimates, the standard elliptic estimates, if you wish, for the Laplace equation to see that you have good estimates up here and down here. And then what happens in a compact set, you declare victory, and you have Fredholm estimates. Okay, so that's, again, a very, very rough sketch of how you go about do this. So I want to say a few words about how you then glue this thing back together. So here I've drawn a picture of one particular corner in my domain. And so imagine this gray thing is the real domain. This W is some fictitious construction of my making that I make some asymptotically conic thing. And I want to take solutions on the asymptotically conic thing and glue them onto the domain, or vice versa. And it's actually the vice versa, which is somehow more interesting. So I'll talk about that. So imagine you have a Steklov eigenfunction U sigma here. So what turns out to be the case is that you can describe the Dirichlet-Neumann map modulo a smoothing operator near a smooth surface. And what that lets you do is it lets you see that near a smooth part of the boundary, your eigenfunction looks exactly like this. Okay, so let me do this for 0 mass, because otherwise I will mess up where the m's go. So let's call this A plus and B plus, and then similarly I have A minus and B minus. Okay, so I have one incoming part of the wave up here and one outgoing part of the wave. I have one incoming part of the wave over here and one outgoing part of the wave. And what you try to do, of course, is you try to, so that works, again, outside of some little ball like this, right? So if I go too close to the corner, I don't have this description. So what I try to do is I try to take my U sigma and put it, I use the honest to God U sigma inside this red ball. So I use the honest to God U sigma here. And then I know that I can find solutions on a smooth domain which match this data, right? On a smooth infinite domain. So I can extend these things by solutions on some smooth infinite domain with exactly this a minus, b minus, a plus, b plus. And the game then, so once you do this extension, is to show that you've got a good enough solution on the infinite domain. And if you have a good enough solution on the infinite domain, you can use the resolvent to see that these guys have to have been related by the scattering matrix. All right, so the key thing is you know a priori that your U near a smooth part of the domain looks like this. Okay, I'm lying to you, of course, because there's an error, but I don't want to talk about it. And you want to do that gluing that way, right? So you take the actual function U sigma near the boundary, near the corner, you extend it by solutions of some nice smooth problem away from towards infinity, and then you have to show that what you get is a good enough solution on the infinite domain. And of course, you can imagine that you can go backwards as well, right? You can go backwards from the infinite domain to get reasonable solutions on the compact problem. Okay, so and here is where it really matters that the operator is non-local. So it's very delicate. It's a bit delicate to handle this, show that this is a good enough solution, but one can do it. Okay, so that's what I'm going to say about what we've done. And I want to just point out some things that you would like to do if you would like to do this in higher dimensions. So one thing is that the gluing becomes substantially more complicated because, you know, waves in one dimension are especially simple, right? There's only sort of two of them. In more than one dimension, you don't have that problem. And the main thing is that, so you don't have a nice Poincare surface to work with in general. Another thing is that, you know, the edge itself might vary from point to point, right? So the angle might vary from point to point. So even though when you zoom in, you sort of get this nice Fourier transform, you have to then deal with the fact that the angle is variable. So as I said, there's no clear Poincare surface. So there's no clear way to separate things from near the edge and far from the edge, which respects the propagation of the problem. That's what I mean by this. So what about vertices? Well, again, David asked about this. One of the main things is that now your singularities extend near infinity, right? So if your singularities extend near infinity, somehow what you want to do is you want to try to put together an iterated structure. So near infinity, you don't have vertices, you have edges. So you do a Fourier transform and you try to push this down. But at the moment, we can't do that. And one sort of technical thing is what happens near the energy M. So that's, I think, not a serious problem. It's just something we haven't handled. But if you want to do higher dimensions, as I said, you have to do all of the values of M. So in particular, you have to do this one that we left out when the energy of the wave is the same as the mass, and that causes some extra difficulties, although it makes some things easier. So those are just a few of the things one would like to do if indeed one wants to go to higher dimensions, which we do. And with that, I will stop and thank you for your attention.
Thank you very much. So we have time for questions. Please speak if you have any questions.
So I'd have one. So there's results by I think Giroir, Colbois, and Hassanejad, where they show that in the smooth setting, the eigenvalues of the Lipschitz-Neumann map are close to those of the square root of the Laplacian on the boundary. I mean, of course, a Dirac operator is a square root of the Laplacian. Would this choice lead, even in, say, the smooth case, to better approximations if we go through this sort of scheme, or you think it's not necessarily
I mean, I think in the smooth case, somehow the pseudo differential calculus does everything you could possibly hope this would do for you. So I don't think you're going to win anything in the smooth case by doing this. Somehow, I guess philosophically, what we're trying to do is, I mean, in a way, to build an operator valued pseudo differential calculus where the operators are somehow the resolvents of the underlying the Fourier transform Dirichlet-Neumann map.
Yeah, I mean, I guess their bounds worked throughout the whole spectrum, not just I mean, both at high energy and anywhere. So
Yeah, so I think at low energy, this is, you know, somehow the gluing together is not going to work well.
yeah, yeah.
The low energy, then you're really dealing with those low frequencies that are traveling very far.
Uh-huh. Yeah, okay, yeah, I see.
Yes, Dennis?
Yes.
Yes, just a short question. You focused on eigenvalues. Maybe I missed this, but can you say something about the eigenfunctions?
Sure. So in principle, one can describe the eigenfunctions as accurately as the eigenvalues, right? So the eigenfunctions are to the same degree of accuracy, they are the eigenfunctions of this, or the sums of the two rows of the eigenfunctions of this Dirac operator.
I have a question. Probably not quite a question, but a remark. You see, in the very original paper about the eigenvalues of the Steklov problem by Leonard Sandgren 70 years ago, in the setting of the problem, there was a weight function in this boundary eigenvalue problem. So you understand that the normal derivative equals the spectral parameter times some weight function, and then the value of the function at the boundary. And I think that if this function is smooth and if it is of constant sign, then your approach can handle the situation without much trouble. My question concerns the case, is it possible to find something about the eigenvalues, the fine structure of eigenvalues and of eigenfunctions for this weighted Steklov problem in the case when the weight function changes sign?
That I think would be quite tricky. I mean, again, because then you're really faced with handling this low frequency stuff for which we don't have a good description. Okay, so I'm not saying no, but I don't see it just like that is the answer.
Well, it must be trickier, but it's challenging.
Yes, yes.
David?
Hi. Yeah, Jeff, just actually to follow up on the question about eigenfunctions. This has been a question we've had for a while. Is it the case that when you have a piecewise smooth boundary, the eigenfunctions Steklov eigenfunctions decay exponentially into the interior?
So I don't know the answer to that question. I mean,
Right.
I would be very, very surprised if that was true. But
So you think they
there
don't?
are some others in the audience who might know the answer to that question. So I would be very surprised if things decay exponentially fast.
But this method doesn't give any particular direct insight into that, or?
I mean, the issue is always the passage from the quasimodes to the, you know, somehow what we're using is a Gaussian problem to know about the eigenvalues, and you know, this doesn't obviously say much about the eigenfunctions themselves in the interior.
Right.
On the boundary, yes, but you know.
Maybe I will also ask something. So in the zero mass situation, as you well know, so there is a phenomenon of exceptional angles.
Yes.
And if we have exceptional angles, then that means that we could have eigenfunctions living on some parts of the boundary, right? So, and by living, I mean, so what passes through the rest of the boundary is exponentially small in sigma.
Yeah.
So I believe this is not possible in positive mass, but maybe it's possible that the portion that passes through the boundary is some power, small power of sigma.
This I don't know. I mean, you know, it's hard for this method to see such fine structure, right? I mean, you lose something by not making the explicit construction, right? You lose this very fine structure that you have when you do this reflection construction, and I don't know. You could repeat the reflection construction. I mean, we've talked about this, but you could repeat the reflection construction for positive mass, and you'll get something, but I don't know offhand what you would get.
Well, my guess would be that special angles would be somewhat different. I mean, they would depend on what mass is.
I mean, I think asymptotically they don't, right? Because one thing in particular that you know at a special angle is that the scattering matrix has to be whatever it should be. I mean, one's, you know, pure reflection or pure transmission. So as you know, as sigma goes to infinity, it must be the same angle. So the actual angles have to be the same. It's just a question of whether you really get this very high quality lack of transmission or pure transmission.
I don't know. It will have to be the same in, I mean, first term will have to be the same, but then you could have some.
But the first term sort of determines which angles it could possibly be, right?
Well, it could be angle, I mean, something exceptional plus O of 1 over sigma, and 1 over sigma could actually matter. I don't know.
Sure, but 1 over, the domain is fixed, right? So there's no such thing as 1 over sigma. I mean, maybe by curvature you could correct away these things. That I could believe.
Okay, but bottom line is you do not know whether you could actually have even some, I mean, proportion going to 1 of
that you know, because as soon as you know the scattering matrix, then you know, okay, where it's going to take me a while. We know the scattering matrix, right? So if this scattering matrix says that you have pure reflection, then you can have, you also get that you have proportion going to 1, you know, on the relevant part of the boundary. So like you can prove that, you know, you will have eigenfunctions which localize here, for example, using this method. Of course, you can do that much better using your method, but
okay, but proportion will be sort of 1. I mean,
the error you'll get is exactly this sort of thing, right?
Okay.
I guess now that I see the slide, I have maybe another question. So I know that a lot of work in the work on polygons was to show that somehow this L was 0.
Yes.
In this case, is there any sort of thing to say about it?
So I mean, we went in the case that the angles are less than or equal to pi, we also can get this sort of relatively cheaply. But okay, I haven't thought seriously about what happens when the angles are bigger than pi. I was happy, you know, I know that those folks worked extremely hard to get rid of this L, but I sort of was happy to get anything.
All right, thanks.
Do we have more questions? Okay, well, we can thank Jeff again for the great talk. We
Thank you
meet
very
again
much.
next week with a talk by Hannah Kim, which we'll share the information about that talk as soon as we have it.